Okay, so you know all this hype about AI just crushing these math benchmarks, right? Like superhuman performance on stuff like Math Arena, and it's been kind of deafening.
Yeah, definitely. But it makes you wonder, right? Like, as someone deep in AI and ML, are these models actually like reasoning mathematically, or are they just really good at pattern matching, just getting to the right answer somehow?
Exactly, and that's what we're going to get into today.
Yeah, we're going deep on a new paper. It's called Get This, Proof or Blue, Evaluating LMS on 2025 USA Math Olympiad.
Love the title.
Right. And it really just cuts right to the heart of it. Do these large language models actually reason mathematically?
So who are these brave researchers taking on this challenge?
All right, so we got Ivo Petrov, Jasper Dekanek, Lubin Boltadjev, Maria Drencheva, Christian Minchev, Mislav Balanovich, Nikolai Jovanovic, and Martin Vetchev. They're from ETH Zurich and INSEE at Sofia University.
Impressive lineup. And what's the gist? What did they actually do?
They didn't mess around. They took state-of-the-art reasoning models and threw them into the 2025 USAMO.
USMO, as in the USA Mathematical Olympiad, right?
So one and only. And anyone who knows that competition knows it's not about multiple choice or just getting a number. It's about proofs. You got to lay out the logic step by step, rigorous, the whole 9 yards.
And they're sharing all their work, right?
Totally open. You can find the full paper and all the extra materials at matharena.ai and on their GitHub, F's for Matharena.
Awesome. So before we dive deep, for those just tuning in, what's the headline? What did these researchers find?
So all the hype about LLMs acing these answer-based benchmarks, well, this paper throws some cold water on that.
Yeah.
When they put these LLMs up against the UPAO, which is all about proof-based problems, they fell apart.
Like, how bad are we talking?
Less than 5% average score across the board. It's rough. They really struggled with basic logic, making assumptions, and just coming up with creative solutions.
Wow, so not quite the mathematical geniuses we thought they were.
Not yet, at least. And this is why this is so important for everyone listening, especially those in AI and ML research. We need to know the real story about what these models can and can't do, especially in a field like math, which requires such deep reasoning.
For sure. So let's dig in. Why are these existing benchmarks maybe giving us a false sense of what these models can do?
Right, so the paper points out a big problem with a lot of the current math benchmarks, and it's kind of ironic because some of them actually use Math Arena.
Okay, how so?
Well, they're great for measuring progress on getting to a numerical solution, right? They often focus on competitions like the American Invitational Mathematics Examination. But the thing is, they don't actually require you to create a rigorous proof.
So it's all about getting that final answer, even if you don't really understand how you got there.
Exactly. You could get the right answer through some clever pattern matching or even just luck without actually grasping the underlying math or being able to construct a logical argument.
Yeah, it's like you can solve a Sudoku puzzle without understanding the rules, just by kind of, seeing what fits where.
Perfect analogy. And in real math, especially in those top-tier competitions like the USAMO, being able to build a clear, logical proof, that's everything. The paper does mention that people have tried to test AI's proof capabilities before, like using tools like Lean, which is all about formal verification.
But there are problems with that approach, right?
Yeah, Lean's great for rigor, but it's super formalized, and it doesn't really tap into the natural language processing that makes these LLMs so powerful. It's just a very different beast.
So it's not a fair fight.
And then there's the focus on constructive proofs, which is fine, but it's just one type of mathematical reasoning. So the big question was still out there. How well can these LLMs actually solve complex problems where you need step-by-step logical proofs written in plain language?
Right, and that's the gap these researchers are trying to fill.
Exactly. And to do that, they picked the 2025 USAMO as their battleground. For anyone not familiar, you want to explain how tough this competition is.
Oh, absolutely. The USMO is basically the ultimate math competition for high schoolers in the US. It's ridiculously hard, and it's the main stepping stone to the IMO, the International Mathematical Olympiad. You have to qualify based on scores from earlier competitions, like the MBA we mentioned.
And it's not just about getting the right answer, it's about writing out a perfect step-by-step proof. These problems require deep understanding and the ability to build a flawless logical argument. There's no room for hand-waving or intuition.
Sounds intense. So how do they actually test these LLMs on the USAMO problems?
Very carefully. They prompted each model to generate a detailed step-by-step proof for each of the 6 USMO problems, and they had to do it in LaTeX, which is the standard for writing math papers.
LaTeX, gotta love it.
Oh, yeah. And to make sure they got a good measure of performance, they ran each problem 4 times for each model just to account for any randomness in the output.
Makes sense. Did they do anything to prevent bias in the evaluation?
Absolutely. They anonymized all the solutions, removing any hints about which model generated which proof. Then they compiled all the LaTeX files into PDFs, ready for the judges.
Okay, so who were these judges, and how did they ensure a fair grading process?
They got a team of 4 absolute math whizzes. All of them were either former members of their national IMO teams or had made it to the final stages of team selection. Basically, these are people who know exactly what a valid mathematical proof looks like at the highest level.
So the best of the best. How did they make sure everyone was grading consistently?
Well, first they gave them super detailed instructions on the evaluation process. And those are all available on their GitHub repo, by the way, just to show how transparent the whole thing was. And before they even touched the 2025 problems, they did a trial run with problems from the 2024 USAMO.
So they could practice and iron out any inconsistencies.
Exactly. They could calibrate their scoring, make sure everyone was on the same page.
Smart. Okay, so these are complex proofs. How did they handle solutions that were partially correct?
Yeah, that's important. The official USMO doesn't release official solutions or grading schemes, so the researchers had to create their own for each problem.
That sounds like a lot of work.
It was. They used resources from the math community, like AOPS, the Art of Problem Solving forums, which is a great online community for math enthusiasts, and all the solutions and discussions they used were double-checked by their expert judges.
So they were thorough.
Oh, yeah. They graded each problem out of 7 points, just like the USAMO, and they specifically allowed for partial credit, just like in the real competition. They even made all the detailed grading schemes public on their website and GitHub.
Very transparent. So the judges weren't just assigning scores, they were also giving feedback.
Right, exactly. Each judge independently reviewed their assigned solutions, comparing them to the grading scheme. If a proof wasn't perfect, they could award partial credit where it was deserved, but they had to write down exactly why they awarded each point, especially for partial credit. And they also had to identify the first major error they found in each solution.
And those errors fell into certain categories, right? You mentioned failure modes earlier.
Right. They categorized the errors into 4 types: flawed logic, unjustified assumptions, lack of creativity, and errors in algebra or arithmetic.
Okay, so enough about the setup. What did they actually find? How did these fancy LLMs do on the USAMO?
Well, as we hinted at before, the results were pretty disappointing. Table 1 in the paper lays it all out. They tested 6 different models: QWQ, R1, Flash Thinking, O1 Pro, O3 Mini, and Claude 3.7. They show the average score for each model in each problem, the total score out of 42, and even how much it costs to run each model.
And the bottom line?
Not a single model got anywhere close to solving even one problem perfectly. The highest average score was less than 5%. And remember, these models are supposed to be superhuman on some of the easier math benchmarks.
Yeah, that's a huge difference. It really shows that getting a numerical answer right and constructing a valid proof are 2 completely different things.
Absolutely. The researchers even suggest that the way these models are being trained right now might not be suitable for tasks that require this kind of precise logic.
So they're good at calculation, but they're not really reasoning.
That's the gist of it.
Okay, so we know the LLMs didn't do well overall, but let's dig into those failure modes. What were the most common mistakes they made?
Well, one striking thing was how different the LLMs acted compared to human mathematicians. Humans tend to have a sense of when they're getting close to a correct solution, even if they struggle. But the LLMs, they were super confident in their solutions, even when they were completely wrong, full of logical errors and unsupported claims.
So they were basically bluffing their way through the problem.
Pretty much. And that's a big deal if we ever want to use these models for real-world math problems. We can't just trust their output blindly.
Yeah, you'd need a human expert double-checking everything. So what were the most common types of errors they found?
The most frequent one, by far, was flawed logic. They were making jumps in reasoning that weren't justified, connecting statements incorrectly, just misinterpreting the whole flow of the proof.
It's like they were trying to sound smart, but didn't actually understand the rules of the game.
Exactly. And even some of the stronger models like O3, Mine, and I would just say things were trivial or standard without actually explaining why. Skipping over those crucial steps just invalidates the whole proof.
It's like saying, well, it's obvious, so I don't need to explain it. but in math, everything needs to be justified.
Right. And then there's the issue of creativity, which is hard to measure, but it was clearly lacking in most of the models. They would try the same wrong approach over and over again, even across multiple attempts, instead of trying different strategies or tools.
So they're not really learning from their mistakes or thinking outside the box.
Not really. There was one model, flash thinking, that did try different approaches, but even those were pretty shallow, and it never really got close to the right answer.
So it was more like throwing things at the wall and seeing what sticks, but without any real understanding.
Yeah, that's a good way to put it. One interesting thing was that most of the models were actually pretty good at the algebra and arithmetic parts. They could manipulate symbols and do calculations without needing help from a calculator.
So at least they got that part right.
Yeah. But there was one model, R1, that made a lot more mistakes in that area compared to the others, which suggests maybe there's something off in its training or design.
So they can crunch numbers, but can't reason. That's a bit of a problem. Now, I heard they also tried using AI to grade the proofs. How did that go?
Yeah, they thought, hey, if AI can generate proofs, maybe it can grade them too. So they took two of the stronger models, O3MyNI and Claude 3.7, and tried to get them to grade the solutions from the other models.
Did they give them any help?
Yeah, they gave them the human-made grading schemes, a correct solution, and even an example of how a human expert would grade a sample solution.
So they were basically trying to teach the AI how to grade like a human.
Exactly. But it didn't work out so well. Both models consistently gave way too much credit, often awarding points for incorrect reasoning. They were inflating the scores, sometimes by like 20 times.
Wow, they were way too generous.
Yeah. And the researchers think it's because the models were getting confused by things like flash thinking's tendency to produce multiple messy solution attempts, or they were giving too much credit to simple but wrong attempts from QWQ.
So it seems like AI is still not ready to replace human experts when it comes to grading proofs.
Not yet, at least.
Okay, so besides all the numbers, what were some of the more qualitative things the researchers noticed about how these LLMs were tackling the problems?
Well, one interesting thing they observed was this thing they called answer boxing. It's basically this weird quirk that comes from the way these models are trained using reinforcement learning.
Okay, what's reinforcement learning got to do with it?
So in reinforcement learning, the models get a reward when they give a clear final answer, often enclosed in a box using latex.
Right, so they learned to put the answer in a box. What's wrong with that?
Nothing wrong with it in principle, but the problem is most of the USAMO problems don't require a boxed answer. But the models, they learned this habit of boxing answers, and it actually ended up messing them up.
Really? How so?
They give an example with QWQ on a problem 5. The model correctly figured out that all even numbers satisfied the conditions, but then it got confused because it was expecting to output a single boxed integer answer. So it just decided the answer was 2 and dismissed all the other correct solutions.
So it was so focused on the format of the answer that it ignored its own correct reasoning.
Yeah, it's like it learned the wrong lesson from its training.
It's like teaching a kid to always raise their hand before answering a question, and then they refuse to answer if they can't raise their hand.
Exactly. And another thing they noticed was that the models were really bad at generalizing patterns. They would see a pattern work for a few small numbers and then just assume it would work for all numbers without actually proving it.
That's a classic mistake. Even humans do that.
Yeah, but humans at least know they need to prove it. The models just treated observation as proof, which is a big no-no in math.
So they're jumping to conclusions, which is not very mathematical.
Not at all. And lastly, they noticed that the models varied a lot in how clear and well-structured their solutions were. Some models, like O3MyNI and O1PRO, wrote their proofs in a pretty logical and easy-to-follow way. But others, like flash thinking and QWQ, were all over the place, mixing up ideas and making it hard to follow their logic.
So some are better writers than others, even if they're not writing correct proofs.
Yeah, and the researchers think this might be because the OpenAI models have had some extra training on writing coherent text, which the other models might be missing.
Okay, so that's a lot to take in. As we wrap up, what are the big takeaways for our listeners, especially those working in AI and ML?
I think the main message is that despite all the excitement about AI solving math problems, we're still a long way from having models that can truly reason like human mathematicians. These LLMs are great at certain things, like calculation and pattern matching, but when it comes to rigorous, proof-based math, they just don't cut it.
And it's not just about the final score. It's about the entire process of thinking logically, justifying assumptions, and being creative.
Exactly. And this research also shows how the way we train these models can actually create bad habits that hinder their ability to reason properly.
So we need to be careful about how we optimize for performance.
Yes.
It's not just about getting the right answer. It's about understanding how we get there.
Right. And the fact that even advanced LLMs can't reliably grade proofs shows that we still need human expertise in this area.
So, yeah, AI has a long way to go before it can replace mathematicians. But this is all important research because it helps us understand the limitations of current AI systems and points to areas where we need to improve.
Exactly. And for our listeners who are deep into AI and ML, this paper raises some really interesting questions, like how can we change the way we design and train these models so they can actually reason logically and construct valid proofs?
What new architectures, training methods, or evaluation frameworks do we need to develop to really push AI beyond just mimicking human behavior and into genuine mathematical understanding?
Definitely something to think about.
Lots of food for thought. Thanks for joining this deep dive. We'll catch you next time.